Thank you very much for the introduction and good afternoon, dear audience. I'm glad to welcome you at our Electromagnetic Day dedicated to filters and passive components. Thank you for your interest. Today I'm going to present you an overview of filter and radio frequency component simulation capabilities in CST Studio Suite. Let's take a moment to reflect on the overall role of electronic systems and devices in our daily life. Let's scroll through our daily routine from the moment we wake up to the sound of our smartphone alarms to the satellite-guided navigation during our commute. Electronic systems have seamlessly integrated into every aspect of our lives. Moreover, the integration of electronic systems is growing fast. We're experiencing so-called Industry Revolution 4.0, with nowadays trends in autonomous vehicles and sensor networks for smart cities, smart factories, new telecommunication standards, 5 and 6G, and of course, commercialization of space like satellite internet Starlink. And each of these applications shares a common thread. They all contain communication systems. They all contain antennas, discussed yesterday at our first Electromagnetic Day, and they all contain passive components sitting just behind these antennas. What are these passive radio frequency components? I'm referring to the passive components like feeding networks with filters, connectors, matching. Other examples are couplers, polarizers, SMD, cavity, microstrip, or high power filters. So all those components that orchestrates the flow of signals. So essentially, any component that carries a radio frequency signal. Why filters are significant? Why we're all here to talk about filters? To answer this, we can simply take a look at the frequency spectrum ranging from radio frequencies up to millimeter waves. These different bands are covered by a vast amount of applications, and today the world of connectivity is pushing the boundaries even into the millimeter wave range. As the frequency spectrum becomes more crowded, the demand for channel filters is ever so high. Communication networks in both terrestrial and space applications are becoming more demanding on the use of this frequency spectrum. In order to deal with strict spectrum needs, filters are used. Depending on the operating frequency and device specification, different technologies for filter design may be used. For lower frequencies, it is fine to use filters, for example, on SMD components. But for high frequencies and small losses, waveguide technology has to be used. The design and analysis of such devices can be challenging, and simulation can play a vital part in the development process. So the main idea here is if you can address 3D filter design, then you can address design of the most passive radio frequency components. And for that, I would like to demonstrate to you CST Studio Suite and its tools capabilities to make life of engineers easier with these regards. This is an end-to-end workflow of designing radio frequency components using products from our portfolio. On the example of a bandpass filter, I demonstrate all the typical design steps, but of course, depending on the application, not all of them will necessarily be needed for your design. Firstly, circuit design and conceptual implementation in 3D need to be done. It can be designed both using CST and its tools, Filter Designer 3D or Fast 3D. Next step is optimization. That is always or almost always involved in the design routine. Then the device has to be studied on the context of its application. The final design might be more complex and might also take into account some physical parameters which were not needed during the concept phase of the design. Therefore, it appears necessarily to perform power handling, mechanical and thermal analysis, and eventually this will bring us to the manufacturing and tuning step with our solutions for additive manufacturing and tuning with Filter Designer 3D. We do have software solution for the entire workflow. And today I will focus on the solver technology highlights. Then I will show you design and analysis tools like Filter Designer 3D is a tool for the synthesis, modeling, and optimization of filters. Fast 3D is a tool for waveguide and cavities. WaspNet is a synthesis tool for waveguide and antenna networks. And finally, Spark 3D, our tool for analysis of radio frequency breakdown. And I will show you as well the optimization technology highlights. And during the presentation, I will also be highlighting workflows that our users can proceed utilizing our tools. So let's start with solver technology highlights. And when user starts to work in CST Studio Suite and creates a new project, first, what can be done is utilizing our project template wizard. Our engineers, after years of working in simulation domain, collected necessary information and employed it in the project template wizard. The templates define simulation settings for you automatically based on your selected application. What settings? Settings such as mesh, boundary conditions, and etc. And here I demonstrate possible selected workflows for radio frequency components. Of course, after selecting a workflow, the project settings can be changed. And it is, I think, a very good start for new users who are not yet experienced in electromagnetic simulations. The wizard will also propose the most suitable solver for the selected application. In order to simulate passive components, the full wave solvers based on time and frequency domains are the most appropriate for the task. These solvers are founded on different numerical methods. Time domain solver is based on finite integration technique. By the way, this technique was developed by Professor Thomas Weiland, who is a founder of CST, and the solver is our flagship solver, and it is very well suitable for devices that have a broad bandwidth, and it is based on hexahedral mesh type. In its turn, frequency domain solver is based on a well-known finite element method. It found on tetrahedral mesh type, and within F-solver frame, there is a fast reduced order model technique that simulates fast at the cost of higher memory consumption, and we can recommend it for filter design. F-solver is a good choice if you simulate highly resonant structures or if your structure has many ports. The eigenmode solver is used to calculate the natural resonant frequencies of structures, referred to the eigenmodes. Classically, the losses are added as an approximation using perturbation method. However, we introduced in 2020 a general solver that is able to include the losses in the system matrix and accurately solve the loaded problem. It is a unique solution on the market and is heavily used for filter design. This also serves the automation offered by Filter Designer 3D, where we even support microstrip models. As you can see, the solver supports lossy and dispersive materials, open and conducting boundaries, and port modes that absorbs the energy. All these allow to achieve high accuracy in determining the loaded Q factor and mode frequency. And now I will touch on solvers that are used for special workflows, like partial RLC solver that is mostly used for EDA problematic, but we also utilize it in a workflow for low-pass filter design. The main purpose of the solver is calculation of equivalent circuit parameters like partial capacitances, partial inductances, and partial resistances. It is based on finite element method, and this method is able to handle highly complex geometries. After simulation is finished, a user can generate a broadband SPICE netlist and later use it in Design Studio as a model with N-pin circuit. It can happen that the presence of electromagnetic fields causes effects from other physics. The losses in materials lead to increases in temperature. The increased temperature can cause deformations to the components that compromises their performance. CST Studio Suite offers multi-physics simulations to analyze these effects. CST Multiphysics Studio uses the same intuitive GUI as other CST Suite modules and seamlessly linked to many electromagnetic solvers. In the portfolio, there are thermal conduction-based classic solver with steady state and transient capability, conjugate heat transfer solver that based on computational fluid dynamics technique to solve all three modes of heat transfer, and structural mechanical solver that can compute structure deformation. Multiphysics solver can be used in a number of applications, including thermal-related detuning. This is a workflow on how to evaluate the detuning of the components due to structural deformation. Basically, the solver excites in the structure excites in F solver. It generates conducting losses, and those losses will be imported into a thermal simulation with the thermal steady state solver. The generated temperature rise will be imported into a structural simulation where the deformation can be observed. And finally, the tuning of electromagnetic response can be evaluated. Conjugate heat transfer solver can be used for a workflow of active cooling system design. The idea behind is when an electronic device is operating, its losses turn into heat. And this heat can be simulated with the thermal solver, and its effects on the device and its surrounding can be found. A user can set up a liquid cooling scenario in addition to the natural convection in the air and compare results. More on that will be in the presentation of my colleague, Michael, in the section Thermal Management for Higher Power Components. So if you're interested in the topic, please stay tuned. Now I'm going to show you a selection of special CST tools for design and analysis of filters and passive components. These tools help our users to simplify design and optimization process and give even inexperienced engineers the opportunity to develop a device. This will be a preview to the next session of our webinar. Therefore, I'm not going to go deep into the details because later on you can see all the details in the parts of my colleagues. Let me start from a powerful synthesis tool for designing different types of filters using the coupling matrix and other classical techniques. Filter Designer 3D, or shortly we call it FD3D. This is how the GUI of FD3D looks like, and what technologies are offered to our users. Firstly, a user can quickly synthesize a filter, simply specifying the desired filtering response. The tool synthesizes ladder circuit for low and high pass responses, and for stop band and pass band responses, a coupling matrix synthesis is performed. The tool offers a large range of useful topologies. It provides fast and robust filter model creation. For the modeling, a user can utilize elements from the CST component library or make his or her own customized library. It allows you automatic parameter mapping and simulation project setup. FD3D has an efficient built-in optimizer capable of utilizing sensitivities for fast optimization. And there is a fast space mapping routine available with model creation workflow. The tool has a unique feature of real-time assistance for tuning of manufactured devices. Various types of filters, and what is impressive, even duplexers, can be designed with Filter Designer 3D. The tool has an automatic dimensioning, which is based on a space mapping routine. When you create a 3D model, this routine starts and you will get optimized results shortly after. All the templates converge now within 5 to 10 full wave iterations. This is a unique solution on the commercial market that can be proven by looking at the convergent plot for highly complex models. Here are the simulated examples with the initial response indicated by the dashed curve. And here is a convergence plot for the models. And look how quickly they converge. That are remarkable results. Deeper knowledge and more details on FD3D you can get today during a presentation of Tionis. And I just would like to show you possible workflows with FD3D. And let me start with the bandpass filter design. So at the beginning, you need to specify a filtering response. Then the tool will propose you suitable topologies and corresponding layout representation that can be adjusted. Now you can select components from the customized library, or customizable library for coupling, resonators, and ports, and execute the eigenmode analysis. Then these 3D components are automatically assembled based on the 2D layout, resulting in a complete simulation model. Finally, the 3D model will be automatically optimized by a space mapping routine based on the eigenmode results and the coupling matrix extraction. When the device is manufactured, there is a possibility to make the final tune using the tuning feature of Filter Designer 3D. The workflow from the previous slide can be applied to a more complex design of multiplexer. Coupled resonator channel filters can be designed using Filter Designer 3D task in Design Studio, and in the same project, a manifold can be placed. The procedure for channel filter design is similar to the previous workflow of bandpass filter design. In the step 6, the manifold design and optimization is executed. After that, channel by channel optimization procedure needs to be done where extraction range is limited around where each passband. And finally, the complete multiplexer design is optimized with Filter Designer 3D goal defined per channel response. More details will be provided during next talk on filter design and optimization. Another possible workflow in FD3D is a low-pass filter design. The workflow is similar to the bandpass filter design with the differences in step 3. Here, instead of eigenmode solver, we applied partial RLC solver to design 3D models for equivalent inductor and capacitor components. Then the 3D components are automatically assembled based on the circuit connection, resulting in a complete simulation model. And it is necessary to carry out final optimization of the entire 3D model. In addition to general purpose solver technologies, CST Studio Suite includes waveguide-based solution tools, Fast3D, and WaspNet. The main advantage of these tools is that they generate results in a very short time with high accuracy. You can see the simulation time here, and let me show you more on that. First, let's talk about Fast3D. It is an efficient software tool for the accurate analysis of passive components based on waveguide technology. It is based on an integral equation technique efficiently solved by the method of moments. It is a model analysis tool where the structure is divided in different subdomains, which can be solved with the most suitable method. Then the different solutions are combined to get the global answer. For instance, the boundary integral resonant mode expansion method is employed for extracting the model chart of complex waveguides with arbitrary cross-sections. The successful combination of such methods ensure a high degree of accuracy as well as reduced computational resources. What kind of devices can be simulated here? It is filters, multiplexers, couplers, polarizers, power dividers, and so on. Using this approach, we can drastically reduce the computational effort. In the schematic environment of CST Studio Suite, we have also introduced a Fast3D blog that links directly to this tool. When opening it, you will directly be taken to the project in the normal Fast environment. And all the parameters are automatically mapped for the block, and therefore co-simulation and design becomes an easy task. Here you can see the example where we connect the fit chain to a corrugated horn antenna and calculate the radiated fields as a result of the cascaded system. To simplify this workflow, we had set up an automatic export from Fast3D to the CST schematic, which generates automatically ready-to-run project, which includes the Fast3D block, the external ports, and the S-parameter task. As you may know, the acquisition of WaspNet was announced at the beginning of 2023. This is a design tool dedicated to very specific application areas based on waveguides in general. It makes use of modal matching techniques combined with more general methods such as finite element. Therefore, every single component can be solved with the most efficient computational technique. Due to its efficient, fast solving time, it is a great solution for optimization of various interconnected parts, like the corrugated horn over here with the detailed feeding network. Fortunately, there are also great design wizards for different applications, such as the horn wizard, the antenna array wizard, or different filter wizards. In addition, there is a so-called designer database, which contains hundreds of different complex designs with parameterized models. And the last tool I wanted to highlight today is Spark3D, a tool for radio frequency breakdown analysis. Radio frequency breakdown refers to two main phenomena. It's a breakdown in vacuum due to electrons that are accelerated by electromagnetic field and impact on the device walls. And engineers call it multipactor. And breakdown in a gas due to electrons that are accelerated by electromagnetic field and impact on the gas molecules, so-called corona discharge. And Spark3D provides a lot of benefits to users. It can provide more realistic breakdown calculation while keeping safe margins. It enables the breakdown analysis of complex components. It supports engineers in the component design process to avoid unnecessary high power tests and increases the reliability of high power components. Here is a list of possible workflows between CST and Spark, such as ionization breakdown analysis, multi-carrier multipactor analysis, radio frequency breakdown analysis under modulated or pulse signals. There is also a Spark3D task within CST Studio Suite, where the task is linked to a simulation project, and you can sweep parameters through Design Studio, and the results will be available in the main tree. Some of the workflows will be presented today by Carlos during our session on radio frequency breakdown in high power components. So please stay tuned again. And I would like to show you an example where we incorporated Spark3D in a broader workflow with high frequency and low frequency solvers. It is a coupled workflow for nonlinear biased ferrites. Imagine you need to design a circulator where the main part of the structure is the field rotation domain containing of two ferrite disks embedded in the dielectric cylinder. In case that the ferrite material is biased by a static magnetic field, the circulator shows a non-reciprocal behavior, which is typical for microwave devices using gyrotropic media. To simulate such a device, a user can utilize biased ferrite electromagnetic coupling workflow. First, a nonlinear static magnetic field simulation is performed to obtain the biasing field for the ferrite material. And then a radio frequency simulation will be proceed. The big advantage is that you can do everything in one environment. Easy to go from one domain to the other with the same model. Then the device is given to the Spark3D for multipactor analysis. And eventually, avalanche effects can be observed as a result. As we already discussed, optimization step is almost always involved in the design routine of filters and passive components. Let me show you the optimization capabilities of CST Studio Suite. CST Studio Suite has a conventional parametric optimizer when you optimize geometry of your design, and the optimizer will find the best value for a parameter depending on the goal of the optimization. The optimizer has a wide range of built-in algorithms like trust region framework, genetic algorithms, particle swarm, classic power, and etc. If you are interested in the algorithm details, I would suggest you to visit CST help page, where you can find a detailed explanation on each of them. And of course, all of them are included in our standard license. A filter response is a very sensitive to small changes in parameters. Traditionally, in F-solver with tetrahedral mesh, all changes in a structure require remeshing. You can make a very tiny geometrical change and your mesh will be rebuilt. In this case, a user can distinguish whether the filter characteristics change due to the geometric or due to mesh change. This we call a mesh noise. CST Studio Suite has a feature moving mesh to avoid this unwanted effect of the mesh noise. If you activate the move mesh, what happens is that there is no remeshing, but the mesh is rather moving according to the small geometrical change. And here is an example of the feature usage in a triplet filter optimization. Here, x-axis is corresponding to the optimizer step, yeah, and the y-axis is a goal value. The red line corresponds to simulation with the moving mesh feature off, and green line when it is activated. You can see that the optimizer can't converge because of the mesh noise. This is a general issue in any code based on finite element method and can be eliminated using the feature of moving mesh. And you can see how the results are quickly converged. So a great feature to use. Furthermore, our trust region framework optimizer exploits sensitivity values for the optimizing structure. This method helps to speed up of the optimization process compared to the finite difference calculation. If the number of total optimization variables grows, the achievable speedup will become even more significant. Here is an example of a multimode filter with 1% fractional bandwidth. Not an easy task to optimize, to be honest. And here you can see how much faster the optimization based on sensitivities converges compared to the finite difference calculation. The optimization of filters involves the high number of parameters. More parameters are involved, more challenging the task is. We already discussed that the filter responses is very sensitive to small variations in these parameters. The classical approach, where the optimization goal is defined by reflection and transmission attenuation, can be not that efficient anymore. Rather than optimizing on the scattering parameters, it is much more efficient to extract the coupling matrix, represented a physical filter topology or a ladder circuit, and optimize the filter directly based on synthesized ideal filter coupling matrix or circuit. The goal of this approach is to minimize the sum of the extracted errors. And CST Studio Suite has a specialized optimization goal for this purpose, the goal type Filter Designer 3D. So far, we were talking about parametric optimization, where you define parameters to be optimized. But imagine a scenario where, for example, you have a transition from circular waveguide to rectangular, and the reflection coefficient in this transition should be suppressed. What shape should be applied as the transition to achieve as less reflection as possible? A basic loft operation is not optimal. A user, of course, can set up a higher order polynomial with many control points and then optimize that, but that will require many iterations and long simulation time. The advanced shaping for this purpose is needed. CST Studio Suite with Tosca tool offers a new non-parametric shape optimization workflow that can solve this problem. Non-parametric shape optimization enables engineers to create design not limited by parametric shapes, but surface areas. After optimization, the mesh nodes of the design space will be moved to form a new shape. The feature is available to our customers since the last year. It is the first commercial non-parametric optimizer for high-frequency optimization. With new licensing scheme, you can use the same tokens for CST and for Tosca. I must say that this workflow brings new means to advanced designing. As an example, you can see the whole monolithic antenna feed chain with the horn antenna, septum polarizer, and cavity filters optimized by non-parametric shape optimizer. More on that will be presented today in the non-parametric shape optimization for radio frequency component session. And just to give you an idea where else non-parametric optimizer can be applied, for example, in PCB technologies, it can be applied for the impedance matching over a short distance. Yeah, or for example, this meandered delay line with small footprint where the reflection coefficient in this frequency band is suppressed from minus 20 dB up to below minus 40 dB, yeah, with this fancy shape of a meander. And it can be as well any type of enclosures, connector transitions, or chip transitions. It's almost endless possibilities. Time flies and we reach the concluding part. And as a conclusion, I would like again to highlight that we have a complete portfolio for design of filters and passive components. We have a wide range of high-frequency solvers for virtual validation of conceptual designs and proven technology for filter design. CST and tools offer efficient optimization capabilities with a special filter optimization based on advanced extraction technique for coupling matrices and ladder circuits. We offer a first commercial non-parametric optimizer for high-frequency applications. Our tools cover analysis of different physical events like power handling, mechanical and thermal analysis. And finally, we provide tools to simplify manufacturing process and final tuning of your device. The new unified licensing scheme provides consistent licensing for simulation across the entire portfolio, which means all of these tools are included. With that, I would like to thank you very much for your attention, and we will be happy to get a feedback from you.